vector transformation from spherical to Cartesian coordinate. First, let's start with a point in spherical coordinate. A point P has three components, r, theta, and phi. R is the distance between the point and the origin. Theta is the angle between the z-axis and r. And phi is the angle between the x-axis and the point on the xy plane. We're also going to use rho from the cylindrical coordinate, which is the distance between the point and the z-axis. Rho is going to help us to simplify the system more and make the transformation easier. Now, to transform a point from spherical to Cartesian coordinate, first, let's take the component of r on rho and z axis. Rho equal to r sine theta and z equal to r cosine theta. Now x equal rho cosine phi and y equal rho sine phi. Now, to transform a point back from Cartesian to spherical, r equal to the square root of x squared plus y squared plus z squared. Rho equal to the square root of x squared plus y squared. Theta equal to the inverse tan of rho divided by z, and phi equal to the inverse tan of y divided by x. For a vector in a spherical coordinate, a vector v also has three components, r, theta, and phi. We're also going to use rho from the cylindrical coordinate, which can help us simplify the vector transformation. To make it easier, we're going to call the component of the point as br, b theta, b phi, b rho, and the component of the vector as vr, v theta, v phi, and v rho. In a point, theta and phi are angles measured in degrees. However, in a vector, theta and phi are the amount of units in a circular motion around a sphere. And the direction of the unit vectors, theta and phi, are along the tangent of the circles. For example, if we have a particle placed at point B and a force of 5 Fi Newton is applied to it, this force is going to be represented around the circle and its direction is going to be along the tangent of the circle. And a force of 5 theta Newton is going to be represented around the circle of theta, and its direction is going to be along the tangent of this circle. Now, to transform a vector from spherical to Cartesian coordinate, both of r and theta have component along x, y, and z axes, while phi has component along x and y axes. To simplify the transformation, we're going to take the component of r and theta along rho and z axes, and then we're going to take the component of rho and phi along the x and y axes. Now, if we take a look on the angles of AR and A theta, we notice that the angle of AR is B theta and the angle of A theta is B theta plus 90. So now we can take the component of both of these unit vectors along the z-axis by taking the cosine of their angles, and along a rho axis by taking the sine of their angles. Now instead of r and theta, we have rho and z, which look similar to the cylindrical coordinate system. Now if we switch to the top view, we notice that the angle of rho is equal to b phi, and the angle of phi is equal to b phi plus 90. Now we can take the component of rho and phi along the x-axis by taking the cosine of their angles, and along the y-axis by taking the sine of their angles. Now, using the trigonometric identities, cosine x plus 90 equal to minus sine x, and sine x plus 90 equal to cosine x, we can simplify the equations. Also, we can replace rho with its transformation equation. Last thing to do is to rewrite the transformation equations in a matrix form and take the inverse of the matrix to be able to convert back from Cartesian into spherical.